Hello everyone and welcome. Today I thought I'd go back and talk a bit again around Module 3 and in particular around things like data files. Data files are a very important part of any of the stuff we do in data science. Almost everything comes from or goes to a file. There are exceptions with databases, but especially in the realm of big data, it's even less the case that we deal with a database. Most of the time we're dealing with files. So jumping straight in, I'm going to go through this a little faster this time because I have talked about it before, but this is kind of a refresher and hopefully I'll add something that we might not have talked about before. So we'll go over a little bit the reading, then talk about some ways of dealing with XML inside of Python and ways of reading files, then similar coverage in R. And then, so jumping straight in, data files. What's it about? Well, it's about the way of serializing information to a disk of some sort, be it a disk drive or be it some sort of cloud storage. Generally speaking, they're in one of two formats, text or binary. There are variations on that theme, though, because XML is technically text, but it's structured in such a way that it becomes semi-structured, verging on being structured. Whereas a binary file may or may not be structured, depends on what it is. So when we talk about deliverable 3, it's very important to be familiar with these concepts because you are to deal with a binary, a text file, and an XML file in both Python and R. And do make sure that you do pretty much all the assignment, and we'll go over that in a little bit as well. Reading, the recommended reading is Python for data analysis, particularly around wrangling with pandas, NumPy, and IPython. Also in R, chapter 12 of the R book. Do keep in mind that there are lots of other resources available to you in the O'Reilly book section, so you might want to branch out and look at some other ones, for example. So into Python. When we talk about reading files, these are the most common ways that you would be reading. This is if you're doing it in a primitive way yourself, rather than using something like pandas. There's variations on the theme, such as reading things that are CSV delimited, a fixed width, which is basically, rather than having a delimiter of some sort, you have you know that from column, say 1 through 5 is a particular field, 6 through 8 is something else, and so on, so that you basically, the placement within the row determines where it belongs. It's an older sort of format, not as popular as it once was. The primary motivation for using it is that you don't have delimiters involved, so it takes up less space. The downside is it's very prone to error, harder to detect whenever data is misaligned, all kinds of other reasons to not do it. So these are variations on the various types of these. The ones that you'll see the most likely is going to be CSV, JSON, possibly HTML, depending upon if you're doing some web scraping, basically. Those are the ones that are typically used. Not to say you might not use some of the others, but the most common, generally speaking, is CSV. File basics. Whenever you're reading a file, you typically, especially if you're using the low-level constructs, you want to use a with block. With blocks are a way of controlling the scope of an object so that whenever you exit the scope, it essentially does the right thing and closes down the thing you were using. In this example you see on the screen, basically if you access the file outside of that indented area around the with section, then it's not going to go well. You'll get an error, right? So it's going to basically say it's closed. And in this particular case, there's no reason to do the close itself because exiting that with block does the close for you. So you can't turn around and read it again after you've closed the file. It's a handles thing. File handles are considered a scarce resource inside of most programming environments. As such, as soon as you're done with them, you should let go of them. Potentially, it would keep something from being able to access the thing you're dealing with. So generally speaking, we release handles as quickly as we can. XML. Well, what is it? Great question. Always a good question to ask about anything. And it's essentially a textual representation of data. Started around 99, 2000, and it was came out of the need to bring structure to documents in a standardized and open way. Prior to that, there weren't a whole lot of good choices for representing data. This was around the same time that HTML was becoming very, very popular. But HTML is great for people looking at it, not so great for computers looking at it, especially the pre-XML version of HTML, HTML before we actually started making things well structured and well formed. So it does allow you to basically represent data using text in a tagged way so that you can easily detect if something is malformed. If the file is not complete, the closing tag won't be present, so you'll know that you shouldn't deal with it appropriately. Two different kind of ways that you'll see tags. One is with an opening tag, something in between it, and a closing tag. You'll also see some that don't have anything inside of them, but may just have an attribute associated with it. You can also have attributes on opening tags as well. So you can have a single tag that has the closing slash there at the end that basically says this is just a tag by itself. Otherwise, you have opening and closing tags that are used to essentially say something starts and something stops. This is important because you need to know how to interact with data and how to read data that's being represented inside of HTML or of XML. Understand that the tags can be literally anything that is defined within the schema, if there is a schema of the XML document. So it's a very free and open sort of way of doing your representation. That being said, there's a few rules you have to follow. There should be a single root node at the root of the XML document, and it is a tree. That means that every node, barring the top node, has a parent, and even the top node has a special parent called a document node. So that's kind of the key concepts of XML. They can be a real pain. That's one thing. Part of the reason is it's not so much that it's XML, it's that it's a tree-like structure that's being represented, and you're trying to, generally speaking, convert it into something that's tabular. If you take it to something that's not tabular, so if you take it to something that's more mathematically graph-oriented, it's not a big deal to deal with XML because a graph is essentially can easily model a tree. A tabular data, though, is much more challenging to model tree structures, so that's where it becomes more of an issue. You do need to know about the XML structure of the document. You can't blindly process it with and extract anything very meaningful out of it. It is possible to do so, but you usually want to know what nodes or what tags, and sometimes you'll refer to them as nodes, what tags is associated with what text and subtext and so on, and subnodes. One of the better ways of interacting with XML is to use either XPath or XQuery. It's a way of extracting information from it in a less painful way. And we'll talk more about that here pretty quickly. So XML introduction, this basically gives you a sense of what a tag looks like. This is an XPath introduction. Sorry, this is how you do XPath queries. And this is so that you can potentially interact with XML in a more structured way. So you as an analogy, perhaps think of it as like, sure, there's probably a way to extract information from a relational database not using SQL. Probably can be done. You probably don't want to do it because it would be very painful. It's a similar concept here. This is a way of finding information in XML documents using a series of essentially queries and specialized sequences of characters that is much simpler than potentially traversing it yourself, right? So good examples here are star basically is a way of saying matching anything, so it's a wildcard like what you would kind of expect. A dot is a single item. / basically says look within from the current node down for anything that contains whatever comes after those slashes. So in this case, a dot / egg looks for something that is an egg element underneath of whatever the current node was whenever that query was done, potentially the root of the tree. And you can also do relative referencing from a given node. You can say, go up to my parent and then do something. And you can also look at the attributes of a given element and see if it has this attribute or if it has this attribute with this value and so on. So that's the basic idea of XPath. So what I did was take an extract of from my EndNote library. EndNote's a reference tracking tool, and exported it out to XML primarily because it was an easy way for me to create a pretty big XML document that has some understanding and some sort of meaningful sort of text. The idea is that EndNote is used to store things like journal articles, reference books, whatever it might be. So the structure is its own sort of structure. I didn't make this up. This is how it saves things. You do have this concept of a database path, which says what database the current record that we're looking at belongs to. You have a source app name. In this case, it's EndNote, with an attribute on there that is both a version and the actual name. So this is as an example. In this particular element, source dash app is a tag, and it has an opening and closing tag, but there's also an attribute on that source app name called EndNote, another attribute called version that has a version of a value of 18.2, and then this is the text of the node, which happens to be the same thing as the name. You also have this concept of a rec number, so that's the record number of this particular entry, and it has a value of 252. Down here is another rec number that has a value of 236, right? So you get the basic idea, hopefully, of it's a way of structuring data. And then the key thing here is that you probably want to get something out of here that is of value. So one thing also to keep in mind is that, especially in the case of this particular file, there's a huge amount of variance within the nodes. Not all records have all nodes, in part because a particular type of reference may have one set of values, whereas a different type of reference may have another. You also have this concept that there's sometimes things that are published have authors, sometimes they have editors, sometimes they are a periodical with a title. Sometimes they're an extract from a book with a certain set of page numbers. Lots of variations, right? Sometimes there's a date, sometimes there's not a date, because it's possible to have a publication with no date. So lots of different variations, and so the key thing there is you can't count on all of the records being present all the time. So one solution to this approach is to use element tree, and then basically do some functions that extract values that are interesting, and also leveraging an XPath expression, and then maybe give an error message whenever something that is required isn't present. So I'll walk through this in a moment in the real notebook, but I'll now talk it through first. The top cell there is basically where I'm setting up the directory and the name of the file that I want to load. I use the os.path to join those two things together to create a fully qualified path. Sure, you could probably do a string concatenation, but you need to remember to check for that closing slash at the end of either the data folder or at the beginning of the file name. So by using the join operator, it does that for you. It takes a look and combines together a path and a file name into something that is a legal representation, and with the appropriate slash embedded. Then we can use this element tree to parse the XML document, and then that gives us a tree. Given a tree, we can grab the root, and then we can iterate through the root, calling these functions that I'm defining up here in a iteration sort of way. So I'm going through all of the records that are off of the root, and then for each one of those records I'm going through their children, which is a record, and then basically extracting stuff of information, populating a dictionary with each one of those, and appending that dictionary to a list of dictionaries. This is a pretty low-level way of doing things, but it's certainly valid and something that you'll often do. There are other ways of doing this with other languages and other tools, but this is a proven way of doing it. And the running notebook for some reason isn't running, probably because I'm not presenting, but I'll go ahead and show that to you here in a moment. So I'll switch over. So the same, the notebook, I updated the path because I moved things around to a different location. So what I just did was loaded the tree to see that. Been working in a different notebook environment. Let's see what that does. Nothing very interesting. All right. So what this does is get root, returns the XML element that is the root node of the tree. So I've defined a couple helper functions here. Get XML path, which takes in a path, a current record, and lets me know if it's not there, if that's considered an error or not. And then the debugging info, so that I can tell you something about what's, you can tell me something about what's going on. So whenever I'm calling this method, I'll give it some information so that we can tell what's going on. And then down inside of here, we actually run through the tree, creating a dictionary, or more precisely, a list of dictionaries that contain this. So each one of these things inside of the squigglies is a record that corresponds to a file in the or a record in that XML file that we're going through. So this is created whenever we do this here, right? So we do a row dictionary that creates an empty one, and then we go through and set the title, the publisher of the year, the record number, and so on with these values that I'm extracting using these functions up here. And so the motivation here is that if something happens negatively, the debug information will give you some information to help you track it down. It turns out that this worked out pretty well, so there wasn't really any need for that. But you do have to be pretty defensive with your coding when you're dealing with XML, because oftentimes it can be rather challenging. So this basically shows you the output. Another approach to do this is using XML to dictionary. And so let's first go through this XML to JSON. So another way to do it is well, actually, that's what I was about to show you, is to utilize XML to dict, and that basically allows you to take XML and convert it into JSON, and then you can essentially deal with that JSON as it's in dictionary format. And that's what this is, name value pairs. The problem you have with this approach is that those dictionaries are going to match very exactly to the structure of your XML document. So in the top example on line 3 there, I've got a tag A that contains a tag B, and just that's all tag B is an empty tag. Then tag C, nested inside of tag C is tag D, and then tag C, and then tag A close. So you've got a tree here of A at the top level, then you've got a B and a C. Inside of C you've got a D, and that's essentially the structure. And so what you get whenever you run it through this, the parse onto the converting it into a dictionary, is the top level tag is tag A. Inside of tag A is tag B and tag C. Inside of tag C is tag D, is a nested dictionary. So you've got dictionaries of dictionaries of dictionaries. Can be a bit of a pain to deal with. So switching back over, I'm going to make sure it's installed by running pip install, and it should tell me it's already there. So here's the example I just showed you. And so you can see this structure, and one of the ways we normally see XML is something like this. And you can do indentation if you can hit the right key. Oh, it's not wanting to do that. So we'll do it like this, right? Tag B. And if you look at XML inside of most web browsers, this is what it'll look like. It'll actually have a tree-like structure to try to make it easier for you to see what it looks like. And that's basically the structure of this information, right? So top level is the tree, and so on. And another way to do that, this is whenever things usually go horribly wrong, but I'll create a simple text file, save it as XML, already done this based upon that error message I got. Apologies, severe weather and the wind caught my attention. So you can see here, Microsoft Edge shows the tree structure nested as I just showed you. Tag A with tag B underneath of it, tag C at the same level as B, and nested underneath that is tag D. So an important sort of concept is understanding kind of the nature of XML. Back through. So in this case, whenever we convert the tags and do the parsing and do a pretty print of the dictionaries, you can see that it shows you that it's an order dictionary of tag A with another order dictionary of tag B and C with another order dictionary of tag D. And tag order dictionary of A is showing you that that belongs to tag A. So it's the same basic structure, but it can get pretty challenging whenever you read something of size. So in this case, reading that in my XML file from earlier, it gets quite cumbersome, and the dictionaries that it creates looks like this. At the top level is an XML document or an XML tag. Underneath of XML tag is records. Underneath of records is record. Underneath of record is a various set of records that are associated with it, which correspond to each one of the items in my repository of information. So another way to do this using the dictionary of dictionaries approach is as follows. And so once you get your dictionary set up, then you need to go through and actually extract the records you care about. The thing that's nice about this approach is that you can basically say that the dictionary that you're looking at, you can basically say, give me this element, and give me this element, and then work your way through each one of those records. So that part's kind of nice, but it to me is not nearly as easy to read as like a dot notation. Or some sort of query approach. So another better way of doing this perhaps is to write a little bit of a smarter function, give it a list of keys that are interested in and with a dictionary, and then we can turn it into something that looks a little prettier, a little easier to understand. So I pass in something that's very close to the dot or the dot that I'm used to dealing with. So I'm looking for these items from that particular interest, record of interest, and so on. So lots of different ways to do this. These are 2 or 3. Feel free to come up with your own variations as well whenever you're going through your deliverable for this assignment. Skim through this pretty quickly. One of the things that I talked about in the past on this topic was don't use try except for flow control, which is what I'm doing here. Rather than encounter an exception, you're better off to try to avoid the exception, because every time you do this try catch, it potentially can be quite slow. Part of the reason is there's this whole interrupt concept and a few other things. Not generally a good idea to do it that way. Better is to basically check to see if something is there. In this case, I'm saying make sure that the length of the list of keys is at least 1 or is 1, and then checking to see if a dictionary contains it or not. So rather than just assuming it's there, check to see if it's there, and generally speaking, it's going to be a whole lot faster. So with that, I'll go ahead and wrap this up. Hopefully this helps. If you have any particular questions, do let me know. That's what I'm here for. Otherwise, stay safe, have a good weekend and holiday. I'll probably still be holding the class anyway, but I understand if no one joins, and I'll talk again with you probably on Monday. Again, have a good evening, a good weekend, and I'll talk to you later.